Well, welcome. Good to see you all. Say hi to our friends on the New York trip.
Hi.
Hi. Okay.
Paul.
So we are going to today talk about, we have a pretty simple plan. We're going to look at homework questions, if you have any. And then we're going to take a look at natural laws. And when we look at y equals ln x, we're going to look at the algebra of natural logs. We're going to take a look at the graphs, and then we're going to take a look at the calculus of the derivatives. So our goal for today is to walk away with the derivative of natural log, and we'll do some examples also. So with that said, do you have any homework questions?
Yeah.
Yes.
Go.
49.
Number 49. What does that one say? 51.
Find an equation for a line that is tangent to the graph of y to the x and goes through the origin.
Okay, this is a great problem because it requires us to do some translation into math, and we're probably going to need to visualize it also. What did you do with the problem so far, Tony?
I found the derivative of the e to the x.
Good. And the reason you found that was that y prime gives you
The slope.
the slope of that line. Good. Now what?
Yeah, 0, 0, 0.
Ah, okay, but here we have to be careful. We do have a point given to us, 0, 0. But this point is not the point of tangency.
No.
It's not the point of tangency. And I know that for a really simple reason. The graph of y equals e to the x doesn't go through the origin. So it's not that the graph goes through the origin, it's that the line tangent goes through the origin. Okay. Good. So now,
How come the y equals e to the x goes through the origin?
it does not. The line tangent goes through the origin. Yeah. So here we have the equation of a line, and it has two characteristics. It is tangent to e to the x, and it goes through the origin. Now what?
Find the slope of the line tangent.
Well, we did. There it is. That's what we know.
I mean, the line is through the origin.
Okay. How do we find the slope of a line through the origin?
I use e to x minus 0 divided by x minus 0.
Ah, very good. I think in order to see what we're talking about, we should draw ourselves a graph. For most people, drawing a graph is a great way to visualize this problem. You probably have the graph in your mind. Okay? And if we visualize it, then the line tangent that I'm talking about is the line that comes from the origin and has just the right slope so that it is tangent to the graph at a point. And you can see there's only going to be one line that does that. And it goes through at some point right here, and that point has coordinates that we don't know, but they are the coordinates x, and the y value is 8. And so Tony says, all right, I can do the slope for this. The slope is e to the x minus 0 over x minus 0. And now, what did you do with that back?
That's where I stopped.
Oh, you're so close. Okay. This is the slope of that tangent line. This is also the slope of that tangent line.
Oh.
So, absolutely. So I can set these two equal to each other. Now when I set these two equal to each other, how can I solve this equation? Yes, why? Yeah, just finish that sentence.
And divide, I mean, what?
Do divide.
Divide. Can I just multiply?
Sure. So what do you get?
E to the x and x equals e to the x.
Good.
And x equals
How?
cancel. I mean, divide.
Divide. Wait a second. Are you dividing by 0?
No.
No, because e to the x is never 0, so that's safe. And lo and behold, I get x equals 1. Well, now that breaks the problem wide open, because x equals 1, therefore, I can come back and fill in that coordinate right there. What is my y coordinate? Which is e, of course. And I have a point. And what about my slope? What is my slope equal to? 1. E. Here we go. Because the slope is y prime, which is e to the x, and x is 1. And so my line is y minus y1 equals slope times x minus x1. Now, actually, we get a little bit of insight if we simplify this, because you'll notice that I can add e to both sides, and I get the line y equals e times x.
Can I just this way? Y minus e equals.
Sure, that's right. But I just found that this compact notation was really nice. Okay. Now, with regard to 51, the spreading of the rumor problem, is very, very similar to 52. And I actually did 52 on a previous video. So I'm going to let you go back and look at problem number 52 on the video, and then tackle 51 again. Okay? I did that from the day that you weren't here. So you want to go back and listen to that. What's that? The C, yeah, right. So that's where watching that video will help. You want the max P prime. That's P prime. Oh, your P prime is a little off here. So in part C, it's 300 over 1 plus 2 to the t, 2 to the 4 minus t. Is that correct? Okay. So your P prime, you had rewritten P as 300 times 1 plus 2 to the 4 minus t to the minus 1 power. I approve. And so for your P prime, you have negative 300 times 1 plus 2 to the 4 minus t to the minus 2. Correct? What you're missing is the derivative of the inside. Right. So you're going to need that before you can find the maximum of it. Does that make sense? Okay. Good. I'll let you figure out the rest. Okay, let's talk natural laws. big idea for today is that logs are inverses of exponentials. And in particular, the natural log, which is the same as log base e of x, has the property that it cancels e to the x to give x back. And this is simply what natural log of x means. It is that function which inverts e to the x.
So ln of e to the
ln x and e to the x cancel each other. Yes. Now this has some important implications for us because we previously, when we talked about exponentials, had three properties of exponentials. And our three properties of exponentials were the product rule for exponentials, the quotient rule for exponentials, and the power rule for exponentials. And what were all of these? Everybody together. E to the x and z to the y is? X plus y. That's it. And e to the x over e to the y? And e to the x to the y? Now, each one of these exponential properties is going to be reflected in the inverse over here. And to get there, what I'm going to do is to assign a couple of symbols. I'm going to say, let's let A be equal to e to the x, and let's let B equal e to the y. And if I make those assignments, then immediately x is equal to natural log A, and y is equal to natural log of b. Okay? Now with that in mind, let's take these exponential properties and let's rewrite them in terms of log properties. I'm going to start with the log of AB, the log of a product. And if I now do the substitution here, then that will be the same as the log of e to the x and z to the y. Use our exponent rule. Exactly so. And because they are inverses, these cancel, and I get x plus y. But what is x plus y? It is natural log A plus natural log of b. And so I arrive at my first of three log properties, which is that the log of a product is the sum of logs. And we call this the product property, or the product rule for logs. And it is exactly the same mathematically as the product rule for exponents, but it is written in terms of the inverse. The log of a product is the sum of logs. Well, this sets us free to do the same thing with other bases as well. So if I have, with regard to the other properties as well. So if I have the log of a quotient, same idea. I can replace a with e to the x. I can replace b with e to the y, and use my product, my quotient rule for exponents. Which has to equals out, it's the same as x minus y, and x is ln a. Exactly so. So that we arrive at our quotient rule for logs. finally, if I take the log of a to some power, now here I'm going to let m be any power, it doesn't necessarily have to be b, right? Or, yeah. Then I can rewrite this as the natural log of e to the x to the m power, which is the same as the log of e to the x. Cancel again. And the log of a to the n is the same as m ln n. This third property here is extraordinarily useful to us, and we're going to be using it a whole lot. This is the power rule for logs. The log of a power is power times the log. Let me get all that down. Good. Okay. Now, here's why we care. These three properties give us really powerful tools for solving equations. And I want to give you a couple of examples. Now, if I were solving this exponential equation right here, I might be tempted to solve it by isolating some kind of exponential and using a log, but the problem is I have two different exponentials. No problem. Natural logs come to the rescue. If I take the natural log of those sides, now I can appeal to the log properties. On the right-hand side, what is this the same as? Exactly. And on the left-hand side, let's go property at a time. Which property applies first? So this is the same as? What's your A, what's your B?
X.
Tell me, what's your A, what's your B? And you wanted to use the product property, right? So the product property has a certain form to it. It has an A and B. What are the A and B that you're looking at? Is A, and what is B? 2 to the x, okay. So now apply the form. See how the form makes it really clear? You don't have to be fuzzy about it if you're using your form and you're identifying the price. Okay? Now, what about this ln of 2 to the x? What can I do with that?
Same with the x times ln 2.
There you go. And what I've done now, by the use of logs, is that I have turned a relatively hard problem involving multiplication and exponents into an easy problem involving addition and multiplication. That's the virtue of logs. They take each operation, multiplication and exponents, and they've demoted one level to the level of addition and multiplication. Okay, now how do I solve? How? I mean, get rid of. I mean, like go and erase it? That's not math. That's right. We're going to have to collect all of our terms that have x in them and leave all the terms that don't behind. Get rid of them. And what's next?
Take out x.
Okay, but what's the word we use? It's not take out. Fact. There we go. Okay. Now at this point, we've actually got a couple of choices. One choice is we could solve directly by dividing it, right? But before we do that, do you see anything that looks like any of our log properties?
Oh. Ln 6 divided by Ln 2.
Okay. Watch your form. You committed the classic blunder. Not ln A divided by ln B. ln of A divided by B. Everybody makes that mistake at least once in their lives. Exactly. ln of 6 divided by 2, which is? Oh, look at that. Look at that. What is x equal to? 1. Really? Let's go back and check. 3 times 2 to the first power equals 6 to the first power. Yep. I guess we could have seen that ahead of time, couldn't we? Maybe. But here's the deal. This could have been a much more complicated example, and we still could have solved it in this way. In fact, let's do that. We'll make one up. There, something like so. Okay? And again, we can logify those sides, as I like to call it. And now that we see the process, it goes pretty quickly. Right-hand side?
X other side.
Left-hand side?
Ln 5 plus X Ln 2.
Yeah, there you go. Once you see the process, it goes really fast, doesn't it? Keep going.
Ln 5 equals to X.
That's the right word. You keep it up.
So, X times Ln 3 divided by 2.
Yep. And now x is equal to ln 5 over ln 3 halves, which is an interesting number. We're just going to leave it like it is. Perfectly valid. So this process of solving with logarithms is actually a very, very useful process. And hopefully you're sold on their utility. We're going to find many more uses than this. We're going to love logs by the time by the end of the year because they're going to do all sorts of nifty things for us, including one on Friday. They're going to make certain derivatives easier to find. Okay, now, that's the algebra. What about the graph of natural log x? To get the graph of natural log x, you need to know one thing, which is the graph of e to the x. Ah, okay. We all know the graph of e to the x. In your notes, sketch the graph of e to the x. And on your graph of e to the x, make sure you put your 3 special points. graph look like? Good. What are your three special points though?
0, 1.
0, 1 is one of them.
0, no,
1, P.
1 comma, just plug in x equals 1. What do you get? Yeah, 1 comma e. And the third special point is not a point, but it is the horizontal asymptote y equals 0. In other words, the limit as x goes to negative infinity of e to the x is equal to 0. These are the things that everybody needs to know about the graph of e to the x. And every single one of those points, every single one of those features carries over into the graph of y equals natural log x. Let's just make one more observation, the observation about domain and range. From the graph, what is the domain of e to the x and what is the range? All real numbers for the domain.
Could the range is greater than 0?
All number. What's another name for all numbers greater than 0?
R and R.
do we have multiples?
Positive or negative? Positive, that's right. These are the positive reals. These are the domain. Excuse me, the range. So is the range. Now, what I carry over into y equals natural log x, we have all of these same features, but they are inverted. So instead of the point 0, comma 1, I will have the point 1, comma 0. Instead of the point 1, comma e, I will have the point e, comma 1. And instead of the horizontal asymptote y equals 0, I will have the vertical asymptote x equals 0. My graph will still increase. It's going to be a reflection about the line y equals x. So my graph will still increase, but it's going to be concave downwards. Like so. Take and reflect over that line.
It says reflect by origin.
No, reflection around, there is no reflecting over the origin, but you can reflect around the origin, or through the origin. That would actually take this graph and turn it 180 degrees.
By origin.
You just did it over a line. See, your hands went over a line. Yeah. So we can reflect over a line or around the point.
So can we say reflect by y equals x?
Yes, that's exactly it. We reflect over the line y equals x. Okay. Excuse me. Okay, now, what about the limit statement? Well, you can see from the graph here that what happens is that the graph of y equals ln x goes to negative infinity as x goes to 0, but only from the right, because the domain is the positives. So we can say that the limit as x goes to 0 from the right of ln x is equal to negative infinity. And the domain and range are likewise inverted, so that the domain of natural log is all positives, and the range is all real numbers. So I want you to notice the 5 features that we have about our graph here. We have 3 special points, 1, 2, and 3. The third point being the vertical asymptote. I think of it as a point at infinity. The fourth being the special limit involving natural log, and the fifth being domain range. These 5 facts about natural log we're going to see over and over and over again. So you want to make sure that you have those clearly. And it's easy enough to have them clearly if you have the corresponding 5 facts on the videos. Okay? Good. Let's do some calculus. What we want is a derivative rule for e to the x. Excuse me, we have that one. The derivative rule for natural log x. And there are 2 ways in which we could get that derivative rule. One is to appeal to the inverse function theorem, because the natural log is an inverse function. And the second way is to use the same method that we've been using for our inverse trig functions. So, let's do both of those. If I want to think of natural log of x as f inverse, then the corresponding parent function that it is the inverse of is e to the x. So that the derivative, remember the inverse function theorem, f inverse prime is 1 over f prime of f inverse. And so using the inverse function theorem here, we would say this is 1 over f prime. What is f prime? Of f inverse. This would be 1 over f prime of f inverse. But what is f inverse? It is natural log x. And what is e to the natural log of x? But 1 over x. Yep. So that what we find then is that the derivative of natural log x is simply 1 over x. Which is profound and kind of cool. There's a second way that we can get the same result by writing the problem in this way. Y equals ln x, what is dy dx? And so remember our method with the inverse trig functions. First we undid the inverse. What do I need to undo the ln x? In other words, if I want to somehow get rid of the ln x, what function do I need to apply to make that happen? Which is e of the x, that's right. So I'm going to raise e to both sides. And when I do, these cancel to give me x. And now I can take a derivative with respect to x on both sides. On the right side, of course, I get 1. On the left side, I'm taking the derivative of e to the y with respect to x. So outside, inside. The derivative of the outside is e to the y times dy dx. Exactly right. So the dy dx is equal to 1 over e to the y. But what is e to the y? It is x. So that we arrive at our derivative rule for natural log of x again. It's the same thing. That's right. It's just looking at it from 2 different perspectives. Pick one. You can pick one. I like them both. This is more elegant. This is a little bit easier to understand. Now, let's do some examples so we can see what we're talking about. The important thing to understand is that the derivative of natural log of splat is 1 over splat times the derivative of unit sign. So, for example, if I have d dx of natural log of 3x plus 4. Outside, inside. The derivative of natural log splat is 1 over splat. Times the derivative of the inside. And when I write that times the derivative of the inside, I'm going to write the multiplication by the reciprocal as just division. And notice how we usually combine those factors, just like that. Does this make sense to everybody? Here's a function that shows up a whole lot. The derivative of natural log of x squared plus 1. Take a minute to try to work that one out. Larry, you look like you have a question. Figured it out? Why don't you take a minute to try to work this out? If you're watching this video at home, you take a minute, pause the video to try to work it out too, and we'll come back in just a minute. Okay, what you got? Very good. All right. So if I were to do it in slow motion, we'd have derivative of natural log of splat is 1 over splat times the derivative of the inside. Which gives me exactly this. Okay, now frequently we're going to see natural logs in combination with other functions. So this is a kind of thing that you might see right here. What derivative rule applies here? Product rule, that's right. So we have first times the derivative of the second plus the second times the derivative of the first. Each one has its own particular derivative. So we have now x squared times 4x. And we have natural log x times 2x. We're going to clean this up as x plus 2x. Now, sometimes, occasionally, you'll see people do clever things using your log properties. So, for example, here it is possible to rewrite this using my power property for logs. Notice how these two are the same thing. Right here. And that's my power rule for logs. So sometimes you'll see that. This one I probably would write like the above right here. This is probably the preferred answer. This is what you usually see. But if you see something like this, don't be freaked out. Don't think, oh, what did I do wrong? Maybe you didn't do anything wrong. Use your log properties to see whether or not your answer is the same as the given answer. Does that make sense? So we'll call this a log property surprise. Okay, let's take a look at another one that's really fascinating. Find the derivative of this guy right here. Very close. What'd you get for your derivative?
Tangent.
Okay, but how?
One over sine x. Derivative of
Mhm. Aha! And we have another name for cosine over sine. It is cotangent x. Really interesting. We just found a function whose derivative is cotangent x. Was not expecting that.
So sine over cosine is tangent.
Tangent, yeah, exactly. Yep, that's exactly right. Let's try it. We've got a prediction. No, no cosine. That's what we got. Hey, I didn't ask for lines. Go away. Here we go. Okay.
Lower cosine x is derivative of x, which is negative
Mm-hmm.
is negative sine x over cosine.
Which is negative tangent x. That's pretty cool. We have a couple minutes. I want to try one more. Let's do it. At first, this function looks like it's pretty horrible. Okay, all right. This looks like a pretty awful function. It is pretty. All right. But now, what is its derivative?
Y over secant x plus times derivative secant x plus tangent x, which is derivative secant x plus derivative secant x,
Which is
which is tangent square x.
mm-hmm. Thank you. Good job. Secant x tan x plus no, it wouldn't be co anything. It'd be secant squared. It'd be secant squared. Okay. Now this looks like a pretty gross derivative, right? What did I do? Oh, there we go. This looks like a pretty gross derivative, and it appears to be leading up to Hegel's law of conservation of grossness. Gross problems have gross derivatives. But Jason sees something.
1 plus secant square x over. Wait. Oh. 1 plus. Wait.
What do you see right here? Secant x. Well, we could cancel it if we had factors. Do you see any common factors? There's a factor of secant x. Let's factor it out. Leaving me with tan x here, secant x in this term, and look at that! Look at that! Isn't that magical? We just found a function whose derivative is secant. Whoa! That's pretty cool. We'll see this again later, because you can imagine that we're probably interested in functions whose derivatives are interesting, right? Yeah. Okay, well, let's call it a day, and I'll see you tomorrow, and we'll talk about general logs tomorrow, which are going to be basically natural logs types of